All right. Hey, everybody. My name's Cameron Hotchkies. I'm here from hex90.org, and I will be presenting blind SQL injection automation techniques. Going to focus mainly on the exploitation of blind SQL injection holes. So thank you for coming. Now, start off fairly easy, fairly simplistic. I will step it up a little bit as we go along. But start off, what is SQL injection? And basically, SQL injection comes down to one thing. It's client-supplied data. It's passed to an application, and there's no appropriate data validation going on to make sure that it's kosher data. So when this is passed in, it goes on to be processed as commands by the database. I'm sure everybody's familiar with this. Yeah? So SQL injection is frequently used to do various things, such as performing operations on the database, which is a vague, nebulous sentence. But then you can bypass authentication mechanisms, read information that probably wouldn't be available to regular user, possibly confidential corporate information, and write information such as new user accounts into the database. Now, there's three general forms SQL injection will take as they're used as attacks to read information. This is what we're going to focus on for the remainder of this talk. Pulling confidential corporate information, confidential information we're not supposed to be getting at from the database, the web application we're attacking. These three methods would take on redirection and reshaping a query. Now, what I mean by that is you've got control over the server. You can start dumping information into the web application, and it's presented in a nice, readable format, easy for you to use and process. Takes a bit of effort if you don't know what the schema is, but usually you can end up pulling that out, having that spit out and displayed to you, and go on from there. But this isn't always possible with every web application you'd encounter. Second main method would be error message based. Now, error message based is the one most people are familiar with and do frequently, and this results in usually a SQL server based attack where you hijack and you send bogus SQL into the query, and it'll display an error message, very verbose, very easy to read, very helpful for the developer, helpful for the attacker to pull information out, and then you can start pulling out the design of the query that goes to the database, design of the schema, and then the actual information. The third one, the one we're going to be focusing on, is blind injection. Now, there's a couple different methods that are referred to as blind injection, so I'll just go over what I'm talking about when I say blind injection. And usually it results in forming queries and not getting much intelligible information from the web server. But you still are getting information at a very slow rate. It's Boolean values, yes or no, but there's information still coming out. All you have to be able to do is interpret the HTML pages regardless of what they're displaying. They might not tell you something immediately, but they are still telling you information. And every form of SQL injection can result in a significant data leakage, data loss, and then move on to data modification attacks. No form of SQL injection is less dangerous than any other. Some take longer than others, notably blind SQL injection. But with a blind SQL injection, we know that we can ask yes or no questions. We're basically playing a game of 20 questions with the web server. I'm sure everybody played 20 questions when they were 4 years old, and they moved on to stop playing it because it was boring. But why would we focus on blind SQL injections? Blind SQL injections probably as common as any other form of injection, but for the most part, from a developer standpoint, somebody who's aware of SQL injections, they're most likely going to be aware of the other forms of SQL injection and say, oh, if I block all the error pages, then I should be fine, I should be safer. We don't like to admit this, but that's what the cut-rate developers out there are doing. They shouldn't be doing it, but they tend to not know any better, and it's a false sense of security on the host system. The other reason to focus on blind injections, if we're looking at automating something, is that it's going to require a larger investment in time to execute a manual penetration against. How many people in the room have performed a blind SQL injection by hand before? How many of those people have carried it all the way through to fully pull real information from the web server? Same people? Okay. It's a bit more than I thought there'd be, but I'll ask you again at the end. Now, the benefits of an automated tool. Said earlier, we're playing a game of 20 questions. And we know we can ask as many as we want. We're not limited to 20, obviously, but there's no reason to stop at 20. We could just keep asking and asking and asking. As long as the web server's there, it's going to keep answering our yes-no questions. But to find the first letter of the username's benign. It doesn't really do anything for us other than let us know if they're really bad in running as SA. To find the first letter of the username, it's going to take 7 requests if we perform a binary search, just for the first letter. Then if we want to find the full username, assume that it's 8 letters long. It's going to be 56 requests, just back and forth to the web server, just asking yes or no questions, performing a binary search. But how do we know it was 8? We had to find out the length of the username. And that's another 6 requests just to find the length. So we're already at 62 requests to the web server. Send it back, wait for network latency, hope you didn't type it wrong, comes back, interpret the yes or no, keep on, wash, rinse, repeat. You're doing this, kind of painful. It's already starting to add up. We'll just assume that it takes about 10 seconds to type this into your web browser. Network latency comes back. So each request taking 10 seconds. And assuming you're not making any mistakes when you're doing these, the 8-character username that we were looking for is taking over 10 minutes now. So as I said earlier, the username really doesn't give us that much. We're going to want to move on to find the schema or the contents of the database. And that's going to take a lot more than the 62 requests. If we want a non-trivial penetration, we're going to want table names, we're going to want column names, and we're going to want the actual data that's stored in the database. So instead of taking 10 minutes, this is going to very, very quickly add up to be hours, days, weeks, months, all depending on the size of the database. And I don't know about you guys, but I'm sure there's better stuff I'd want to be doing than sitting at my keyboard, entering it in, yes page, no page, moving on. It's a bit tedious. Now, it might sound simple to write a tool that would automate this. Just crank one out, a few shell scripts in Netcat. But if we want a more comprehensive tool, a tool that works on more than just one singular web application, that we don't have to come back, we don't have to keep messing with, we don't have to keep rewriting every single time, it's going to be substantially more complex. Now, I'd like to show you a sample web application we wrote to do testing with. It's an online bicycle store. It's a pretty ugly web application, and if it was a real web application, they'd probably go out of business really quickly. But it has the basic elements of what a web application would have. You'd have the title, you'd have a banner, you'd have a random menu on the side. And this is the catalog we're looking at here. The person who brought it up was looking at bikes. They're looking at a Schwinn bike, and the Schwinn bike's $30. That's another reason they might go out of business shortly. But it's generally, like, there'd be more stuff that's going into a web page, but this is just a quick example of what it would look like. So as you can, I don't know if you can see that, but in the address bar, the product ID is 2. So mess around with that. That might be our injectable area. So we've made one slight modification. We just appended and 1 equals 1 after the numerical 2, and we get the same page back. Realistically, if there was input validation going on, if it was safely going to the database, it shouldn't be returning any information on this. But since it is going to the database, it's returning the same page because 1 is still equal to 1. It's always going to return true, and it's returning the ID number 2, we're assuming. If we move on, modify it a bit more, put n 1 equals 0. Last time I checked, 1 wasn't equal to 0, so fairly safe to assume that's going to be a false page, and it does come back that way. It comes back with no rows found, indicating we've got a blind SQL injection that we can now play with. There might be an error based here, but we were looking for blind, and we know we can work with it. We'll always have a true page, we'll always have a false page if we're performing this form of blind SQL injection. Now, I mentioned earlier that to find the username, it would take 7 requests and then 56 requests. And basically what we do when we're doing that, because I'm going to be referring to this later, is everything can pretty much be broken down into integers when you're pulling it out of the database. If it's text, convert it to ASCII. or convert it to Unicode, you somehow convert it to a number that you can pull down. If it's an actual integer, you can pull it, move it to a number. If it's some other data format, convert it to ASCII, then convert it to the integer you're dealing with there. But we can always pull down integers from the database. So we select a range, usually start with 0. If we don't have an upper level or a lower level, we can basically just move along, asking yes or no questions to the web application, go up exponentially. So is it greater than 0? Is it greater than 2? Is it greater than 4? Greater than 8? Just keep going until we hit an upper limit. And we now know that it's in between that number and the previous number that we went to, because we knew it was greater than 16, but it's less than 32. And from there, you can just start binary going down, splitting it in half, until you narrow in the exact number, just by asking, is it greater than this number, greater than this number? Comes out fairly easily. So this method can be repeated to pretty much pull all of the information very slowly, but it can still come out of the database. And this is how we're going to be performing the blind SQL injections. Now, the main problem that we deal with, though, when we're automating a blind SQL injection is we know now how we can pull all the information out. Just find the number that's associated with the data we're trying to figure it out. And we know that there's a true page. We know there's a false page. It's always going to return one of those unless the server decided to die on us. But we know that we can recognize a true page versus a false page. On the bike shop example, it would have that ugly green table, and it would have the price, and it would have the bike name. And if it was a false page, it would have the no rows found. Pretty easy for us to see. But as people, we always take pattern recognition for granted. So natural reaction was, can't we just do string comparison? Because that's what the web page basically comes down to being, very long string. We have a known true, we have a known false. Compare it to the known true and the known false. But the problem is we can't really do that. Because the whole point of a web application, the reason companies are rolling out web applications is they want dynamic content. And it would be pretty naive to assume that the only dynamic content in the web application is the actual information that we're pulling out. There might be random other stuff coming into the web page, either times, rotating banner ads, possibly email this page to a friend. That one pops up fairly frequently in web applications because they want everybody to advertise their site. But that's just a hyperlink, and it's going to change every time we make a request, which is the URL we're requesting. So obviously that's going to throw a problem if we're just doing string comparisons. String comparisons do work fairly well when you're doing an error-based injection tool, but for blind, it just doesn't work very well. So take another look at the Bob's Bike Shop example. This was the false page that we saw earlier. It's the exact same page, but if you look right above the no rows found, that's the time. Every single second we do an injection, that's going to change slightly, and it'll throw off the string comparison. And if you look underneath, it's telling you which page you asked for. Not going to happen very frequently unless it's something where it's to refer this page to a friend or bookmark this for later. And that's going to be changing every single time we do something, because at the very end, we can see that it's added the end 1 equals 0. So first possible solution that we went through several solutions when we were trying to write the tool, because this is all based around a tool that we wrote. And the first solution we thought of doing was just a keyword search. But the problem with this is that every time you do a test against a different web application, there's always going to be different keywords. It could be based on a dictionary and automatically detect it, but then depending on what information you're pulling through the web application, depending on what's being displayed, it could get thrown off. It's really not a successful way to do this, because every time you're going to have to rewrite the tool or reconfigure the tool, and there's better ways to go about it. We want to minimize the amount of interaction the users have when they're working with the tool. So second possible solution might be an MD5 sum. A lot of people, they immediately see this. They're like, oh, I'll just take an MD5 sum of the web page and just use that in memory and compare the MD5 of the true page versus the MD5 of the false page to the MD5 of the unknown page. But the way MD5 works, the reason MD5 is used, it's a message digest, and it's not just MD5, it's any cryptographic digest hash, it's designed for small inputs, small changes in the input, to create very, very large changes in the output. Because if somebody changes one word in your message, you want to know immediately that it's changed slightly. And it's going to just completely change the entire MD5 sum if just one character changed. This is an example of that. Took the home page for Google. It's not a very complex page. Everybody's familiar with it. And I just basically took the index.html, saved it, took the MD5 sum of it. And that's the blue lines you can see there on the graph. Then I went to the title block, changed the word Google to Hoogle. It's just one letter, increase the ASCII value by 1, and it throws the entire graph off. It's not close. It's not even near being close. And you can't tell what part of the HTML file changed. That was just by one letter. And we're worried about random stuff changing regularly. So MD5 is not going to be the way we want to proceed with this. So if you're thinking about using that, if you want to write a similar tool, it's not going to handle the changes well. And it might work on some web applications where there's less dynamic content, but it won't be comprehensive. There's going to be other web applications out there that will have the dynamic content. MD5 is actually worse than a string comparison, because at least when it's a string comparison, you can tell at what point they stopped being the same. So talking with one of my friends, figuring out how we're going to do this, and he said, why not just use a text different engine? I'm sure most of you have used a text different engine of some kind before, either diff or even Microsoft Word. It'll highlight the changes in documents, highlight informational changes. This word, it was changed to this word. This paragraph was moved down 3 lines. But there's a lot of work that goes into doing one of these, and there's a lot of information that we don't care about, because when it comes down to it, it's a yes or a no. That's the only real answers we care about. So there's going to be a lot of effort wasted while writing the text difference engine, and we're just going to throw that away in the end, so it doesn't really do us any good to work through it. So fourth possible solution, there's a lot of different things you could do, probably wouldn't want to do. The fourth possible one is to represent the text, represent the HTML the same way a browser would, as entities in a tree data structure. And then after you've created the HTML tree, you go through and you look for differences in the shape of the trees, if different entities are there, if it comes down and then there's a table with one cell, if it's a true page, and then there's no table, all of a sudden the tree structure is going to completely change, and you would be able to identify the true page versus the false page. But problem with that is that if only non-markup data is changing, and that's most likely possible, then there's going to be no way to proceed with the automation. If the tree structures are the same, then it looks the same to the parser, at which point you'd have to start comparing the actual text of the entities in the tree, and you're going to have to move on to work on a slightly different way to do it. And it's easier in practice to implement an XHTML parser than a realistic HTML parser. There's a lot of really, really bad coders out there who write really, really bad HTML. And this isn't a new thing. This is like 1994. People started writing really bad HTML, and they're still doing it. And when it comes down to this, it's going to make dealing with this, representing it as a tree, very complex. And you have to start dealing with bugs, because you're designing code that's taking advantage of bugs out there. So it's fairly safe to assume that their HTML code is going to be as bad as their backend code. So I'm through showing you stuff we decided not to do, and going to get on to the actual method we're using. And what that is a linear representation of ASCII sums. What I mean when I say that is you basically look at the HTML file as a list. It's a sequence of elements delimited by carriage returns, which is the same way we look at it. And you take each line of text in the HTML file, take the ASCII value of each character, sum it up, and that way for each line you get a single unique number, and, well, unique to that line, I guess. But it's just a single array of numbers that form up a signature. And if you look at the graph, you can see that unlike the MD5, which is, this is the same 2 pages that I showed you for the MD5, Google and Hoogle, and a small input variation is going to be a small output variation. You probably can't see it on that page there, because I can't see it on this laptop here. But the only thing that changed was number 2, where it changed by 1 line. So something that was small and insignificant to the actual page doesn't show up very well. It gets hidden amongst the rest of the details, which is what we're looking for, because we're trying to focus less on small changes and focus on the important changes on the page. So since we found a method that we're going to use, move on with the ASCII sum signatures, we need a way to compare the signatures of the true pages, to compare the signatures of the false pages, and once we have that, get the signatures of the unknown pages and be able to cast it as a true or a false. So to do this, we're going to need base cases. It's fairly straightforward. We just have to get a set of trues and a set of falses, and so that we can make later comparisons. But we already know what a true page should look like and a false page should look like at this point, because when we've identified the injection, we've identified what a true looks like and a false looks like. And so if we have a tool that's taking place after the injection's been detected, we can just use simple base cases. 1 is always equal to 1. 1 is never equal to 0. So you have the URLs down there where you do something similar to that, where you just simply append an always true, find out what that page looks like, append an always false, you know what that page looks like, and you've got a set of base cases to work with. You could use different base cases. These ones are just fairly simple to work with. So if you remember back near the beginning, showed you Bob's Bike Shop, showed you the true page and the false page. This is the signature set for the true page and the false page. The true one's in blue, and you can see how it spikes up there, and that would be where it was giving you the ugly green table with the Schwinn bike information, the price, and then it comes down and finishes off the page. But for the page that had no rows found, it simply goes up a bit less and then finishes off the page. You can see how the page endings are the same, just sort of offset. But the page signatures are different enough that we wouldn't confuse them. Now, just in case you're wondering, Bob's Bike Shop is admittedly complex, and this is a more realistic signature set. This was taken off of an exploitable commercial web app out there. I don't remember which site it is, so don't bother asking at the end. But this is just a small subset of the actual signature that would be available for our real live commercial web application. And as you can see, there are still differences. There's a lot of noise going on, but this is the one part where they would change enough that you could be able to differentiate a false page from a true page. So now that we've figured out what a true page looks like, we figured out what a false page looks like, because we want to find the trues and the falses to get the integers. We need to figure out how we're going to compare the true pages and compare the false pages. Because minor changes in the textual content, minor changes in the actual HTML that comes down the wire, they're going to be small changes in the output. But the problem is they are still changes in the output. We can't do a straight comparison with them. So why not use a tolerance? We saw both of those examples. There was a point where they were substantially different from each other. So if we allow for very, very small changes, like if it changed by 1 ASCII value, that's going to be such a small change, allow for a small percentage change, and then we can easily work that in, and still hopefully with the 2 different signatures be different enough that we can move on with the comparisons. So you just take the absolute value of the known versus the unknown over the known, and that gives you the percentage that you're going to deal with. And you use that for comparisons. If that works out, then you register that as equals. Otherwise, say it's not equals, and you've hit a page miss. So the Bob's Bike Shop example I showed you earlier, hopefully you can see the tolerance bars there. You can see as it starts off, they're almost identical. So there's where it should be the same, it's falling into the small tolerance band. That's what you work with. And once they start to substantially diverge, they diverge enough that the tolerance band doesn't really allow for the two different signatures to get confused with each other. Now, what I'm showing here on this graph is a tolerance band of about 10%, I believe. In a realistic example, like that really noisy example I showed you of a real signature set, you're not going to want to use much more than a 0.01% tolerance band. Otherwise, we've had some bad experience with false positives and false negatives. So you're going to want a very small tolerance if you're going to be using a tolerance altogether. But nothing's perfect. So there are problems with a tolerance band comparison. If that's all you're going to be doing, it'll work most of the time, but there's a lot of unnecessary comparisons going on. If you look at this page, it's not until section 10, or line 10 on our signature set that they start to diverge. And for every single every single page hit we get back, that's 10 comparisons we don't need to be doing. And we're going to be doing a lot of them. So it seems like a bit of a waste of time. But it also doesn't take advantage of known garbage data. Stuff that, like, as people looking at the web page, we'd be able to just discard, say, it doesn't matter to us, we don't care, this has nothing to do with our injection, yet the computer's just going to keep comparing it. So why not find a way to get around that? So this is where we implement a subtractive filter. What we can do is we can identify sums, the actual values in the signature, and look at conflicting base cases. Look at a true signature, look at a false signature, and if the values are the same in the true signature as they are in the false signature, why bother to even look at them later? If they're the true in the beginning, if they're equal, then they have nothing to do with our injection. So cancel them out. From Bob's Bike Shop, we've already canceled out half of the comparisons we were doing because they had nothing to do with our actual injection. And what this also helps us with is something that's going to change dynamically, unrelated to our actual injection, but it changes slowly enough that when we gathered the base cases, they were the same. Well, they're not going to be compared in the future because they were already identified as not being relevant to the injection that we were trying to exploit. But why stop there? We added a second filter to it because the subtractive filter is good for pulling out information that we don't care about, but there's still going to be junk data that slips through where they're not equal to each other, because if it's changing quickly, then we won't get that equivalence between the two. If between the 1 equals 1, the 1 equals 0, they've already changed, then it's going to not be caught by the subtractive filter, even though it has nothing to do with the comparisons we're dealing with. So this is where we implement an adaptive filter that can remove the junk data that throws off our results. The only thing here is that it's going to require more than one of each kind of base case. Before, when we started, you'd have a single 1 equals 1 for the true, a 1 equals 0 for the false. Now you're going to want to gather a bit more of that, but it's not that big of a deal because when we're actually exploiting a blind SQL injection, we're going to be firing off hundreds and thousands of requests. So an extra 5, it's not that big a deal. So here's two samples that should be identical. We're asking the database is 1 equal to 1. Yes, true. So it's going to return a true page. Then we ask the database, is 2 equal to 2? Once again, it's true. So if it's saying true to both of them, they should end up being the same page in theory. But we find that there's 2 more elements in the signature that have changed. Since this is Bob's Bike Shop, we know that it's probably most likely the time at the top that's going to change every second, and probably the line with the address being returned to us, because we've asked 1 equals 1, and that's in the address. We've asked 2 equals 2, And so it's a different address, even though it's the same end result. So we can filter that out, and all of a sudden, this junk data that would throw off our results is no longer an issue. So the benefits of using an adaptive filter like this is the tolerance, we're not really sure if we even need it at this point. You can keep using it if you feel that it's going to be helpful because there's stuff that the filters are going to miss. But you can always just re-implement the filters if both of them fail. And that gives you a bit more, that cuts down on your false positives, cuts down on your false negatives, because if it's gone through the subtractive filter, it's gone through the adaptive filter, and it doesn't match either, then maybe you need to reevaluate what your subtractive and adaptive filters actually are, regather your base cases, because maybe a substantial part of the change took place. Let's say if you were SQL injecting /dot. Every 15 minutes, you're going to get a post, then a duplicate in half an hour, and it's going to change the actual contents of the page. So, but it's not going to be fast. You'd want to reevaluate everything. So you'd build that into the tool. But this will allow us to remove anything that's we can immediately tell is unrelated to the actual injection we're performing. So I mentioned we wrote a tool. At Hex 90, we wrote a tool we called Squeal. And it was sort of where all the research that I'm sort of talking about took place. So everything I've mentioned was basically the growing pains of writing the tool. I wrote it in C#, and I wrote it in Linux, which is kind of weird for some people. But there's a Linux version, and there's a Windows version of it. If you are interested in running the Linux version, I'd recommend running Mono 1.0 or later. It was a bit buggy until the 1.0 came out. But both of them seem to work fairly well. And it's free for non-commercial use. Now, before I get the boos and the beatings, it's free for Black Hat attendees as well. So everybody in this room, everybody at the conference gets a free copy of Squeal to run and do whatever they want with. And so one of the benefits of it is that it's going to export all of the data, all of the formats related to Squeal are XML, very easy to read, very simplistic, because I don't want things too complex that I get confused. And you can easily format it using XSL or whatever you want for presentation to clients or bosses. Here's an example of the data this Squeal uses. This is for the actual blind injection that I was describing earlier. What it will do is it will you'll have to initialize your base cases every time you use it, but it'll save the results from the base cases and the signatures, so you only have to initialize once, and it should save all the information that's relevant to the actual injection. So we'll jump over to it and give you guys a brief run through of how it works, what it looks like, if you feel like playing with it later. I've already loaded it up because it's faster than doing it by hand, but it still takes time to run. This is a web application running on the local host. And so you just specify the address right about here. Specify that you want to get request. You have the option of commenting out the end of the query in case there's extra junk there that's going to mess you up. You can use HTTP proxy if you feel like doing this anonymously, but everybody's here is legitimate, so we'd never want to use anonymously. Then all you simply do is add each of the form parameters in the box down here, identify whether or not it's injectable. Usually, you'd have the one injectable parameter. If you have multiple injectable parameters, it'll just take advantage of the first one that you enter in. And you also have the option of adding HTTP headers if you need that to help you authenticate to the web application. Once you've entered all the information here, simply hit the Initialize Injection button right here, and this gathers your base cases for you. Once you've done that, you can do fun things like retrieve the username. That's fairly quick. The web app we're running is running as SA, which is fun. And I've already gone through and gathered the table names. We've got a users, sales rep, product, customers, tables in the database that we can play with. What you would normally do is the tables would start off being empty. You'd load the table information. It would gather all the tables, the IDs, which is how SQL Server recognizes the tables in the database, the number of records available to the tables, and then once you've got the table information, you can gather all the column names. And so this will give you the column name as well as the data type that it stores the information as, which can be broken down as an integer as well. So once you've got all this information, you get to the fun part. Right here, this is the downloading records, downloading the real core of the information in the database. Yes? Yeah. Now, would that be the database, the web application to the database? What this one actually does is it just grabs the system_user in the, so it's just sort of a canned set of queries that would do that. I don't know if that would return the NTLM password. Do you know? Pardon? Yeah, it does, like the only point of entry is the web application for this tool. Pardon? Okay. I'll get to you right after we finish this. Basically, though, once we do this, we can start downloading the records, create the data file that we're going to use, save it, and going to want the credit card number, going to want the name, going to go have fun, drink it tonight, and start it running. Now, it's going to take a while, so I'll get back to the slides, and then we'll come back to it in a couple of slides, and hopefully it'll be done. So, gathering the table information. You saw the table information was already loaded into Squeal, but this is basically the methodology as to how the tool goes about doing this. It's just a couple canned stored procedures, or not stored procedures, canned SQL syntax that the tool will append to all of the queries. So it starts off, goes by getting the ID number for every table from the sysobjects table. So all you do is start off by finding out how many tables are in the database. Once you found out how many tables are in the database, you find out the IDs, starting with the smallest ID available, move up to the largest one available, and just cycles through that. Anything in the bold there is the value that's going to be changing as we're doing these integer searches, as I mentioned earlier, because we can pretty much, since we're breaking these down into integers, just increase the search value exponentially, then cut it down, and it pops right out. For the second one, you'd increase the search value up and down, and you'd cycle through each table ID in the list. Now, once we've got the ID numbers of every table, we can go on to get the table's human recognizable name. Start off by finding the length of the name. It's the same way we do the length of the username, where you just grab the length, cycle up, cycle down, zero in on a number. And once we've got the length of the name, we know how many iterations we're going to have to do, go through and find the ASCII value for each character in the name, goes up, goes down, finishes, pulls the information. For the fields, it's fairly similar to the tables. Start off by getting the count of each of the fields or columns in the database. Then once you've got, for each table, because you have the IDs to work off of, this way you don't have to mess around with textual names, which might mean you'd have to either use the char function or apostrophes, which you want to avoid. So you go by the numerical type table ID. Once you've got the table ID, you go in the column IDs. One note, if you are writing a tool like this, don't use a 32-bit integer for the table IDs, because they're pretty big. Had to deal with that one once. And so once you've got that, the column IDs, for SQL Server, which is Squeal only works with SQL Server at the moment, just in case anybody's going to be asking this later. Most of the research was done off of SQL Server, although it could be adapted to work with Oracle or other databases where you have access to sysobjects tables or similar tables. So you've got the column ID, cycle up, cycle down. It's going to be a lot smaller because it's just the sequence number of the column in the table. So once you found the ID, go through, same as the table, get the length of the name. Once you got the length of the name, find each character's ASCII value, move on from there. The only real difference when we're pulling out the column information is the fact that a column information is going to include the data type, which is what we're going to need later if we're starting to pull out real information from the database, because we want to know how we're going to go about pulling it out. So what you would simply do is, in SQL Server, you figure out the data type, and you can convert the data type to an integer, because that's how SQL Server represents it internally. This is a chart. This is in the slides that should be on the CD. It should be in your printed black hat proceedings as well. So just the chart of the numerical values for the SQL Server or MSDE's data types. Save you guys a bit of time if you want to look it up later. So let's see if this is done. Looks like it's done, so we can go here, load up the XML file in Internet Explorer, and hopefully you guys can see that. Can everybody see that? Or should it get bigger? Bigger. Heard somebody laugh, so I think somebody could read it. Okay, can you read that? Hopefully. What that is this is the XML output of the columns and the data that's been pulled from the database. As you can see, I was unfortunately one of the victims that bought a bike from Bob, but I'm not alone. Mr. Johnny Long, Jeff Moss, Dave Litchfield, and Robert Morris, all their credit card information. So it's not really their credit card information. But it'll pull the information out, and it'll save the primary key value in case that's not one of the fields that you wanted there, and store that if you want to work with it later, in case you're curious of how it worked, because it's going to need the primary key as it pulls the information out. And then it'll just store it in this XML file. Once again, it's fairly easy to format, easy for presentation. If you're doing a pen test and you want to run it on a client, you just format it out, print out a big binder of their database, and they'll love you forever. DBA will. So to do all of the queries that it would take to have pulled out that information, pull out the table schema information that was already there, as well as the username, which was really only 2 characters, so it's not that much. But all of that was going to take over 2,700 HTTP requests. So if you use the 10-second rule that we talked about earlier, which is fairly realistic if you're doing this by hand, it's going to have taken over 7.5 hours to do this by hand. So this is where I repeat the question. Who out there in the audience has done this by hand before? All right, bit less. But yeah, it's brutal if you're doing this by hand. It's painful, it's tedious. So using a tool like this makes a little bit more sense. Whether it's this tool or another tool or one you write yourself, you're not going to want to do this by hand. And it can be automated, so why not? And what I pulled out, that was 4 entries in a database. That's not that much, especially it's a small demo database with a very, very small schema. So if you want the entire contents, if you're being greedy, you want everything available for a real production web server, real production web application, including stuff that probably shouldn't be available to the web application, but for some reason is, then it's going to be a lot larger in the amount of queries it's going to ask for, and it's going to take a lot longer to run than 7.5 hours. And that's nonstop. You had to be there, typing it in all day, hoping to die, getting more coffee, but you didn't have time because you're still there typing. Brutal. So, wrote the tool, works for the most part. It's still not perfect. Nothing really is here, but there are some shortcomings, either by choice, by design, or by my ineptitude. And so the first one, this may or may not be a shortcoming, depending on your view on it. User agent's hard-coded. I don't allow anybody to change that through any of the interfaces in it. You could probably reverse engineer it and rewrite it. It's in .NET, so it's not that bad. But for the most part, if anybody wants to download the tool and just run it and start being a badass out there, then you could block the user agent from ever hitting the web app, hopefully. And that'll take out probably 80% of the people who don't know what they're doing. And second problem with a tool like this is it's noisy. I mentioned earlier that 7,500 requests going against the web server that are most likely logged. So the log files grow really, really quickly. And if you're hitting a very large database, there's a real possibility that you might fill up the hard drive with the weblog requests before you actually pull all the information down. Because for every bit that we get, you're adding an extra 25 bytes to their server, maybe more, and just fills up, fills up. And it's fairly obvious if anybody looks at the logs. It's just like, and 1 equals 1, and 1 equals 0, and 2 equals 1, and 2 equals 0. And then it just goes on to these extreme SQL statements in the get string. If it's a post, it's just going to be the same page, and the guy will just think he's really popular. But another valid thing that could throw the way Squeal does it with the ASCII sums, that method's not perfect either. The sums could be easily poisoned with random seeds that throw in extra carriage returns because it's carriage return delimited. If you saw Samuel's talk yesterday, one of the features was inserting random data into there. And if that happens and throws off the carriage return count, then it may confuse the adaptive filter. So that's one possibility for throwing off a tool like this, although might not throw off other tools to deal with it differently. And the other thing with this is it doesn't really lower the bar. I've talked about automating blind SQL injection, but I've talked about automating the exploitation of it. So you still have to be able to find the blind SQL injection hole. It's not that hard, but some people still aren't that skilled, so they won't get much out of this app. And the final thing that might mess it up is if the HTML has no carriage returns. This comes back to the problem I mentioned earlier with bad coders out there, people who aren't anal retentive with their designs. And the HTML gets outputted, and it's just one very, very, very long string. So if you were opening it up in Notepad or VI or whatever, it just goes on forever, and you shake your fist at the guy and hope he dies. But it's out there. And so if there's no carriage returns, which is how this delimits it, then it's just going to be one value in the signature, and chances are it's going to get thrown off by the adaptive filter because it'll say, oh, these pages are changing every time, so get rid of that one element, and now you've got a 0-element signature for the true and a 0-element signature for the false, and that doesn't work out very well. We thought about working with a forced carriage return, but the problem with that is it still throws off the data. You have to assume, okay, I'm going to insert carriage returns if the line exceeds 160 characters, or it exceeds 300 characters. But you know somebody out there is going to make a 400-character line that's supposed to be there, and it'll just mess up your tool as it tries to go through. And it'll start shifting. If you remember the graph, the tail end of it was always the same, and it should keep the same shape. But all of a sudden now it's been thrown off. And depending on where the dynamic content is, if that's the line that you're forcing the carriage returns in, it'll mess up whatever tool that assumes this. If you really want to deal with the no carriage returns, you're probably going to want to go back to the tree parser that I mentioned earlier. It's going to be a lot more work to probably implement that way, but then you're dealing with these guys, so that could be a second stage attack if the ASCII signatures isn't working for you. So, in conclusion, this isn't limited to blind SQL injection, and it's not limited to this form of blind SQL injection. Now, when I say other forms, everybody has their own view on what this term actually means, because I've talked to a couple people and they're like, oh, you do this and this, and it's like, oh no, because that's not what I'm meant. But so there's different ways to do it. There was a white paper written about reverse engineering the actual query that was going to the database. If you decide you want to know what is included in the query that's going to the database, then you would use that to do almost error-based, but not quite error-based, because it would give you the nice clean error. It's like an error has occurred and blah, 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 system administrator notified, whatever. And so you get that, or you'd get the right result that's like the picture of the bike. And so that's still a yes or no question. You just basically mentally wrap a different question as a wrapper question around it, saying, is this syntax valid? And then you insert something, and if you get the bike, yeah. If you get the pretty error message, then it's a no, and you can simply move on from there. Keep in mind, if you ever want to do something with web application profiling, MD5 is not going to be the right way to do this. It's going to trip up as you hit dynamic content, and there is a push for web applications to become more dynamic. That's how the web application developers maintain their job and justify their existence. I'm one of them, so it's okay. And the same techniques could probably be used for anything else that could be done with blind, as long as there's 2 web pages. I haven't done a lot of work with it, so if anybody else wants to work with it, feel free. The XPath or LDAP injections could probably be automated that way. And the big thing has nothing to do with my talk, but it has to do with SQL injection, and this drives me nuts, is that not enough people are still doing this, using parameterized code in an appropriate fashion to call stored procedures. If you don't want to use stored procedures, so be it. Make sure you're using the parameterized code appropriately. If you're not using a language that supports this, switch languages or find a better way to do this. There's a lot of lazy programmers out there, and whether or not you're a developer, you might know a developer, and if they don't do this, slap them, hit them, throw stuff until they start doing this, because it's really bad, and there's been mechanisms for doing this properly for a while now, and there's really no excuse for people to not be doing this. So I've included 3 main white papers that I used during the research. So if anybody wasn't too up to date on SQL injection or blind SQL injection, I'd really recommend reading these. First 2 are from NGS, mainly focused on error-based SQL injection. Fairly verbose, very well written. And the 3rd one is from SPI Dynamics on blind SQL injection. And this is an extremely good paper if you're still not sure what the hell I was talking about for the past hour. Check this out, and basically it's those techniques automated, and then you'll be like, oh yeah, now I see what he's talking about. So this tool isn't available yet. It should be up on the web on Monday, but you guys should all have it on the conference CD. Both the Windows and the Linux versions should be included on the CD. And opening it up for questions now. Yes? Overall, yes, they'll be shorter, but there's always a chance that where they wouldn't be. If it's a the question was, the question was, there's an easier way to do it, yeah, but that would mean, in general, an error page is going to be shorter than a true page, but the thing is that that's not always the case. So if you're dealing with something, like for the most part, you'd probably get 70, 80% on something like that. But then there's still going to be situations. And when you're not dealing with an error page, when it's the page thinks it's returning what it should be returning, but now it's just returning an empty value. So it's going to be a little bit shorter, but it might not be substantially shorter. Or if it's realized that all of a sudden it's like, oh, no records were returned, it writes you a paragraph or like copy of War and Peace, deciding to tell you everything you could do to talk to the system administrator to find out why your account's been suspended or whatever. So, yes? Um, for the most part, I don't believe it does any encoding directly on it. The only type of filtering or like intelligence as far as encoding goes is, for the question was, sorry, I keep doing this. The question was, is there any type of encoding that goes in the tool to allow for filtering of, or to prevent filtering of data by the web application? And the answer basically is no, other than the fact that it avoids using apostrophes wherever possible by using the char keyword, but it wouldn't be that hard to create signatures based off of it for an IDS or something like that, to just, oh, look, Squeal's being run, shut it down, don't trust this guy. Yeah, well, it supports proxies, no problem. So if you want to do that to do the encoding, then by all means, that would be a good way to do it. Yep. Probably more successful than if I'd coded it anyways. So, yes? Pardon? Yes. Right now, it's just SQL Server, but the plan is to start working on Oracle next, now that we've got the SQL version running. And we're going to try and set it up so that it'll actually work on plugin-based interface. So if we mess it up, somebody else wants to write it, then that'll be an option too. But Oracle's next in line for building up the queries and stuff like that. I'm not sure what's going to happen after that one, but we've already started talking about developing for an Oracle tool as well. Any? Yes? In theory, it wouldn't be that hard. The tool doesn't support anything like that, but it could easily be, you could, instead of delimiting by, because basically it's a split statement in there, so it's just split by carriage returns instead of commas or whatever. So you could say delimit it by /brs and add that in. So it doesn't support it, but I could work on it and get it. Yeah, no, it's a good idea. It's a very good idea. Is there any other questions? All right. Well, thank you, everybody.